Seismic performance of steel fiber reinforced concrete beam column joints under the variation of column axial load. Abstract: this study presents a finite element investigation of steel fiber reinforced concrete beam column joints under cyclic loading with the variation of axial load. The aim of the study is to investigate the influence of axial load variations on the seismic behavior of steel fiber reinforced concrete (Sfrc) beam column joints. Nonlinear finite element analysis with a damaged plasticity model in ABAQUS/standard is adopted. The finite element model is verified using experimental results conducted by other researchers. 6 Sfrc specimens with different column axial load ratios and a 2% volume fraction of steel fiber were simulated under reversed cyclic loading. The parameters investigated are maximum load carrying capacity, stiffness degradation, energy dissipation, and failure mode. The results indicated that an increase of column axial load has a valuable influence to delay the initiation of cracks and damage accumulation, slightly improvement of the joint stiffness, and improves the energy dissipation of joints at the initial stage of loading. Moreover, when the axial load level increases up to 50% of the column capacity, no cracks observed in the joint area and no change in the maximum load carrying capacity. However, when the axial load level of more than 50% of the column capacity, the cyclic stiffness decreased slightly due to the deterioration caused by crushing of concrete in column. Thus, the results revealed that the increase of column axial load improves the confinement of steel fiber reinforced concrete beam column joints. However, a threshold limit could be required. Keywords: beam column joints, steel fiber reinforced concrete, cyclic loading, axial load variation, nonlinear finite element analysis. 1. Introduction. Moment-resisting reinforced concrete frames are assemblies of beams and columns connected by beam column joints. These frames should be adequate ductility, strength, energy dissipation, and stiffness to resist the seismic loading without collapse. 1. Several studies 2-7 have established that Sfrc is capable of improving the seismic behavior of reinforced concrete structural members, such as shear walls, beam column joints, and axial members subjected to seismic loads. Based on earlier studies, the application of Sfrc considerably improved the shear strength 8,9, the flexural strength and ductility 10-12, and fracture toughness 13 of the reinforced concrete members. The use of Sfrc as a minimum shear reinforcement for beams has been permitted in ACI 318-14 following the research study by Paramontesinos 15. An experimental study of such joint behavior is not feasible to assess the effect of several parameters involved in joint behavior. Furthermore, because of the difficulties in integrating the compressive column axial loading in the experimental setup, it is common practice to assume the column axial load to be zero or constant in most of the researches. 16. Nonlinear finite element analysis, however, can be viewed as one of a convenient and reliable solution to investigate such effects. In this study, the seismic behavior of Sfrc beam column joints under the variation of axial load is carried out using the finite element software ABAQUS/standard. The finite element model is validated against existing Sfrc beam column joints tested by Choi and B12. After validation of the model, 8 Sfrc beam column joint specimens under cyclic loading is investigated by varying the column axial load ratio. 2. Research significance. The use of steel fibers in RC members can offer a positive influence. However, due to the high expenses and restrictions of specimen fabrication, experimental tests for reinforced concrete structures need spending a great amount of time and money, especially countries not have advanced laboratories. Moreover, due to the complexity of incorporating the column axial load in the experimental test setup, it is common to assume the column axial load to be zero or constant in most of the investigations. 16. Hence, further study needs on Sfrc beam column joints with the variation of axial load. This study provides the finite element results on the seismic performance of Sfrc beam column joints with the variation of compressive column axial load. 3. Finite element model. A three-dimensional, 3D, Nonlinear .NITE element model of Sfrc beam column joints are developed using ABAQUS/Standard 17 by considering both geometric and material nonlinearities. 3.1 Element types, meshes and boundary conditions. A three-dimensional linear 8-node brick elements, C3D8R, were employed for modeling of steel fiber reinforced concrete and steel plate. Two-node linear three-dimensional truss elements, T3D2, was used to model steel reinforcements. A mesh size of 40 mm is used for the whole geometry for all elements. To apply the boundary conditions identical to the reference experimental test setup, the nodes at the surfaces of the lower and upper column ends are attached to a reference point using the coupling constraint. The loading steel plate at the tip of the beam was constrained in Y direction for the cyclic loading application. The boundary conditions, mesh and were set in the model as shown in Fig 1. 3.2 Interactions between components. The embedded approach was adopted for the interaction between the Sfrc and the steel reinforcement, which enforces displacement continuity and the perfect bond between the two elements. The interaction between concrete and reinforcement after cracking was incorporated only in a simply.ed way using the tension stiffening in the concrete model. This was adopted to approximately simulate load transfer between cracks over the rebar 18,19. The interactions between the surfaces of the inelastic and elastic solid bodies representing the concrete material and the loading steel plate is modeled using tie constraints. 3.3 Load application method and cyclic loading protocol. In this study, the loading on the beam tip is adopted as in the experimental setup by Choi and B12. Additionally, the ACI 374-20 recommendation for reverse cyclic loading protocol is used with the same loading history as reported in the experimental study, as showed in Fig 2. The reversed cyclic load is applied in terms of displacement-controlled step, where the displacement is determined from the drift ratio, %, based on the following expression. Drift ratio, %, equals, times 100, 1. Where, and are the applied displacement at the beam tip and length of the beam from column face to the application point of the cyclic displacement, respectively. Analogous to the test loading condition, two loading steps are .NED in the finite element modeling. The .RST step is the axial load step where the axial load is applied at the column top surface as a pressure load in a load-controlled mode and kept constant in the second step. Then, the reverse cyclic loading is applied in the second step on the beam end at a distance of 1,800 mm from the beam column interface. 3.4 Analysis approach. Nonlinear finite element analysis of the beam column joint specimens was performed in ABAQUS/Standard by considering both geometric and nonlinearities with viscose regularization. In the static general analysis procedure of structural components, an appropriate solution algorithm is needed to solve the nonlinear equations. Newton-Raphson equilibrium iteration provides convergence at the end of each load increment with intolerance limits for all degree of freedoms in the model 18,19. Automatic increment with a large number of increments and a small time step size are used to improve the convergence rate. 3.5 Material modeling. The concrete damaged plasticity, CDP, model available in ABAQUS was adopted for the nonlinear material behavior of steel fiber reinforced concrete in compression and cracking in tension. The CDP model uses the concepts of compressive crushing and tensile cracking to represent the inelastic behaviors of quasi-brittle material. The plasticity of the steel reinforcement and the elastic behavior of the steel plate were considered in the finite element modeling. The CDP model is active for the analysis of concrete structures under monotonic, cyclic, and dynamic loading 18,19,21. The CDP model was developed by Lubliner et al. 22 and later refined by Lee and Fenves 23. In uniaxial compressive loading, the CDP model performs linearly up to the value of the initial yield is reached, then followed by a stress hardening and strain softening beyond the ultimate stress. After the calibration of the CDP model parameters on the experimental specimen, JNR2BTR, tested by Choi and B12, the considered parameters in the CDP model for all specimens were presented in Table 1. According to ACI 544.3 R9324 report, normal weight Sfrc with a fiber content up to 2% by volume has a density in the same range as normal concrete of 2306 to 2403 kg/m3. Also, according to the ACI 544.1 R9625 report, the density and Poisson's ratio of Sfrc are generally taken as same range as to those of normal concrete when the volume percentage of steel fiber is up to 2%. In this study, the Poisson's ratio and density were taken as 0.2 and 2400 kg/m superscript 3, respectively, for steel fiber reinforced concrete material modeling based on the above recommendations. 3.5.1 Modeling of Sfrc in compression. Several investigators have proposed models for the characterization of the compressive stress-strain behavior of Sfrc 2631. All have relatively similar approximations of the Sfrc behavior under uniaxial compression. Generally, steel fibers only have minor effects on the ultimate compressive strength of concrete, slightly increasing or decreasing its magnitude, depending on the characteristics of the fibers 2532. However, the use of steel fiber in concrete significantly enhances the descending branch of the compressive stress-strain curve. Due to this, a compressive constructive model of Sfrc differs other than normal concrete compressive model was still employed. In this study an attempt was made in the validation section from different Sfrc compressive stress-strain model and the model proposed by Lee et al. 31 was adopted. Based on this constitutive model, the behavior of the Sfrc was assumed to be elastic linear up to reaching 0.4. After this point, the plastic behavior was defined using the following equations. 7. Where is the uniaxial compressive stress of Sfrc? Is compressive strength of Sfrc? Is the initial elastic modulus of Sfrc? Is the uniaxial compressive strain of Sfrc? 0 is strain of Sfrc at peak stress. Is the volume fraction of steel fiber? Is length steel fiber end? Is the diameter of steel fiber? As mentioned in previous section, hook steel fiber with a length of 30 mm and a diameter of 0.5 mm was used in this study for consistency of the referenced experimental study by Choi and B12. Equation 8, which is proposed by Ouet al. 33, was used to estimate the compressive strength of Sfrc because it gives an approximately equal value with the referenced experimental test data reported by 12. Equals, plus 2.35. 8. Where is the compressive strength of normal concrete? Is compressive strength of Sfrc end? Is the fiber reinforcing index which expressed as equals 9. The ultimate strain for Sfrc was set to the value, equals 0.02 according to the work reported by Wang 34.4, 0.5%. 3.5.2 Modeling of Sfrc in tension. There are a number of different constitutive models developed by researchers to represent the tensile behavior of Sfrc 2735-37. In this study, the model proposed by Locke and Xiao 36 was employed to represent the tensile behavior of Sfrc. Furthermore, a number of researchers 38-39 conducted a nonlinear finite element analysis of fiber-reinforced concrete elements by using this model and found the Locke and Xiao 36 for Sfrc material behavior in tension resulted in precise predictions. The uniaxial tensile stress-strain relationships of Sfrc by Locke and Xiao 36 model shown in Fig.3 and which expressed by x 10-11 4 0 = 12. Where is the ultimate uniaxial tensile strength of Sfrc? 0 is the corresponding ultimate tensile strain. Is the residual strength from the strain 1, as shown in Fig. 3. These values are defined by 40 as follows. 14. Where is the fiber orientation factor in a three-dimensional, 3D, case? Hanant 41 used the value of as 0.50, Soroshian and Li 42 taken as 0.405 and Locke and Xiao 36 taken as 0.50 for slabs and 0.405 for beams. In the present work, is taken as 0.50. The value of modulus elasticity of steel fiber. 200 GPa used in this study recommended by Amin and Gilbert 43. According to Locke and Xiao 40, the initial tangent modulus of Sfrc in tension and in compression is assumed to be equal, and the ultimate tensile strain, 0, corresponding to, expressed as 15, where 0 is the initial tangent modulus of steel fiber reinforced concrete. For hook-type steel fibers, the value of bond stress 6.8 MPa is used in this study as suggested by Lim et al. 44. Equation 16, which is the correlation between splitting tensile strength and compressive strength of Sfrc proposed by 45 was used to estimate the splitting tensile strength of Sfrc. However, the CDP model requires the uniaxial tensile strength as an input. Therefore, the relation is given in EQ 17, based on Eurocode 246 recommendation was used to convert the splitting tensile strength into a uniaxial one. 3.5.3 Steel reinforcement and steel plate modeling. The mechanical properties of reinforcing bars were employed to represent the longitudinal reinforcement and shear stirrups in numerical modeling were exactly the same as the material properties reported by Choi and B12 as presented in Table 2 and Poisson's ratio of 0.3. Note: is specified minimum yield strength, is measured yield strength, is yield strain, and is ultimate tensile stress. The tensile stress strain of reinforcing bars was assumed to be elastic with corresponding Young's modulus and Poisson's ratio. The nonlinear behavior of steel bars was modeled as a bilinear elastic plastic material using a strain hardening ratio of 0.01, as recommended by Kishlakov and Miller 47, and it is used by many researchers 48,49. The typical bilinear stress-strain model of reinforcement bars is shown in Fig. 4. In order to avoid the concentration of stresses on the concrete, premature failure or cracking at the cyclic loading point, a 20 mm thick steel plates were used at this loading point. This loading steel plate is modeled with elastic properties, steel material having an elastic modulus, ES, of 200 GPa, Poisson's ratio of 0.3, and no yielding strength to avoid any premature failure in the steel plates. For model validation, existing steel fiber reinforced concrete beam column joint specimen which experimentally tested by other researchers was used for model validation. 4.1 Details of experimental specimen used for validation. To investigate the behavior of Sfrc beam column joints numerically, the performance of the nonlinear finite element models developed in this paper are validated against experimental specimen tested by Choi and B12, namely JNR2BTR was selected. According to their study, the specimen represented the first floor exterior beam column joint, at a scale of 2/3, subassemblies of a 10-story office building. The specimen, JNR2BTR, is designed without any hoops in the joint panel region and made with a 2% volume fraction of steel fiber in concrete, but the beam and column are reinforced by hoops based on ACIASCE Committee 352-50. Hook steel fiber with a length of 30 mm and a diameter of 0.5 mm was used in the experimental study in consistence with ACI 318-51 as shown in Fig. 5. The columns had a cross-section of 300 mm x 300 mm, with a height of 3000 mm. The beam had a cross-sectional dimension of 250 mm x 375 mm with lengths of 1900 mm up to the contraflexure point in all sub-assemblages. The reinforcement details and geometry of the validated specimen is displayed in Fig. 6. Furthermore, the geometrical properties, variables, and details as presented in Table 3. The compressive and indirect splitting tensile strength for the Sfrc reported in the experimental study are presented in Table 4. In experimental study, beam column joint specimens were loaded using a hydraulic actuator under cyclic loading applied tip of the beam as a displacement controlled. The axial load was applied on the top of the column. Note, P is the applied axial load to column. Is the cylindrical compressive strength of the concrete steel fiber concrete? Is the area of the column? Is the diameter of reinforcement bar? Is width of beam? H is overall depth of beam. Is width of column? H is overall depth of column, and is volume fraction of steel fiber. Note, 1 mm equals 0.0394 inches. 4.2 Finite element model predictions. As described before in the summary of experimental work, the specimen, JNR2BTR, which were experimentally tested by Choi and B12, was selected to validate the developed finite element model. The accuracy of the nonlinear finite element model was evaluated by comparing the nonlinear finite element analysis, NLFIA, results of this specimens with experimental result in terms of load displacement response and failure pattern. 4.2.1 Load displacement response. The load displacement envelope curves obtained from nonlinear finite element analysis compared with the experimental results of the specimen JNR2BTR are displayed in Fig 7, AB. The higher stiffness in finite element models may result from more microcracks, reducing the stiffness of the experimental test. It is obvious that more microcracks are present in test, while finite element models do not include these microcracks. 52. The load displacement curve predicted by the NLFIA shows a very good agreement with that of the experimental result. The average maximum load obtained from the NLFIA analysis was 3.35% lower than the average maximum load reported from the experimental study, refer Table 5 for comparison. From the above figures, the ABAQUS models show the envelope curve precisely. However, the hysteretic loops of the ABAQUS models as compared to the test results exhibit a fat pinching distance as expected from the embedded method of concrete and reinforcement modeling. This pinching distance clearly described that the tension stiffening approximate consideration of bond slip effect in the modeling due to the adoption of the embedded, perfect bond, method to simulate the bond between reinforcements and concrete. The error in overall model accuracy predicted by NLFIA is compared with the test result and presented in Table 5. In order to express the overall model accuracy, an accompanying average underestimation or overestimation of the NLFIA, the error, %, and mean model accuracy m, %, estimated based on the relation given in Behnam et. 2018, and et. 19. It can be seen in Table 5 that in all cases, the model prediction of the joint diagonal cracking load and maximum load lead to an error below 5%, which once again shows that the nonlinear finite element simulated response of the specimens was in a very good agreement with the results reported from the experimental study. Specimen 4.2.2 Failure pattern. Fig 8 and Fig 9 shows the comparison of crack patterns in specimens JNR2BTR obtained by the nonlinear finite element simulation and reported from the experimental study at the maximum load and at failure load stage, respectively. These responses clearly demonstrate that there is a very good agreement between the experimental and nonlinear finite element prediction crack patterns. This numerical result also further approves the accuracy of the nonlinear finite element model and shows strong capability in predicting the general behavior of both the reinforced concrete and steel fiber reinforced concrete specimens. Therefore, the model can be used as an effective and reliable numerical tool for further studies on Sfrc beam column joints. Based on the comparisons, it can be concluded that the developed finite element model can successfully predict the seismic behavior of Sfrc beam column joints with high accuracy. 5. Parametric study. 5.1 Specimens description. The level of axial load is described as a percentage of, where, is the area of column cross-section and, is compressive strength of steel fiber reinforced concrete having 2% volume fraction of steel fiber. The column axial load is applied as pressure compressive stress. 8 different column compressive axial load levels, 0.0, 0.05, 0.1, 0.2, 0.3, 0.5, 0.7, and 0.75 times, were modeled and simulated. Based on the amount of axial load ratio, these 8 specimens designated as JS4-Sfrc2A0, JS4-Sfrc2A05, JS4-Sfrc2A10, JS4-Sfrc2A20, JS4-Sfrc2A30, JS4-Sfrc2A50, JS4-Sfrc2A70, and JS4-Sfrc2A75, respectively. The column and beam cross-section, length and reinforcement details are identical to the validated specimen, JNR2BTR, except the number of stirrups in joints panel zone. The joint reinforcement details of the parametric study specimens are as shown in Fig 10. The description of the specimens with axial load variations are reported in Table 6. Note, P is the applied axial load to column. Is the compressive strength steel fiber reinforced concrete? Is the area of column? Is diameter of reinforcement bar? Is width of beam? H is overall depth of beam. Is width of column? H is overall depth of column, and is volume fraction of steel fiber. 6 Results and discussions of the parametric study. The main parameters investigated in this study due to the effects of axial load variation on the joint seismic behavior are load carrying capacity, crack patterns, energy dissipation, and stiffness degradation responses under cyclic loading. 6.1 Effects of column axial load on load carrying capacity. The hysteretic loops obtained from the nonlinear finite element simulation of specimens with different column axial load ratio are shown in Fig 11, AH. The increasing of column axial load level from 0% to 20% of column capacity resulted in an increase of some extent, approximately 1.3%, of the peak load carrying capacity of the specimens. However, when the axial load level of more than 20% of the column capacity, the lateral strength deteriorates slightly due to the development of greater compressive shear stress in the joint area. As displayed in Fig. 13, the specimens with column axial loads exhibited early strength than the specimen simulated without axial load. The specimen which has not column axial load, JS4-Sfrc2A0, recorded its average maximum load carrying load capacity of 103.46 knots. The specimens JS4-Sfrc2A05, JS4-Sfrc2A10, JS4-Sfrc2A20, JS4-Sfrc2A30, JS4-Sfrc2A50, JS4-Sfrc2A70, and JS4-Sfrc2A75, are exhibited their average maximum load of 103.59, 103.95, 104.79, 104.23, 104.38, 104.35 and 104.74 knots, respectively. G. S4-Sfrc2A70, H. S4-Sfrc2A75. Figure 13, Load displacement hysteretic responses of all simulated specimens. The average maximum load carrying capacity of the specimens under different column axial load levels are exhibited in Fig. 12. 6.2 Influence of column axial load level on damage and failure pattern. 6.2.1 Joint cracking behavior. Fig. 13 to Fig. 14 shows the cracking pattern in the joint observed at different stages of loading for specimens with different axial load ratio. The specimens with higher column compressive axial load level were established to delay and reduce the occurrence of cracking in the beam column joint area in compared to the specimens simulated without column axial load and under low column axial load. Fig. 13 illustrates the joint cracks observed in the specimens at the first loading cycle of 1.0% drift. In specimens under low axial load, JS4-Sfrc2A05 and JS4-Sfrc2A10, the diagonal cracks appeared in this loading stage were very low intensity compared to the specimen without axial load, JS4-Sfrc2A0. However, no joint cracking was observed in the specimens under axial load levels more than 10% of the column axial capacity, greater than 0.1. This confirmed that high axial load would delay the formation of joint cracks and it was beneficial for joint confinement. G. JS4-Sfrc2A70, H. JS4-Sfrc2A75. Fig. 13, joint cracking behavior of the specimens at 1% drift ratio. With further increase of loading cycles, the specimens without axial load, JS4 Sfrc2A0, and under low axial load levels, JS4 Sfrc2A05 and JS4 Sfrc2A10, exhibited a significant diagonal shear cracking in the joint core zone and flexural caking in the beam plastic hinge region. However, only flexural cracks observed at the edges of the beam column junction extended into the beam plastic hinge region for specimens with column axial load level more than 10% of the column capacity. For example, joint cracking patterns at the first cycle of 5% drift ratio showed in Fig.14. G. JS4 Sfrc2A70, H. JS4 Sfrc2A75. Fig.14. Joint cracking behavior of all the specimens at 5% drift ratio. 6.5 Effects of column axial load on stiffness degradation. Fig 15 illustrates the peak-to-peak stiffness of all specimens from each first cycle out of 3 loading cycles at each drift ratio. The specimens with higher axial load ratios were found to have a higher peak-to-peak stiffness than specimens with low axial load ratios in early drift ratios. It was observed that stiffness degradation of specimens had a critical influence only in the initial loading cycles, and the stiffness values after a 2.5% drift ratio of loading were approximately in the same value in specimens with different axial load ratios, but specimens under very high axial load are slightly greater stiffness degradation than specimens with low axial load. Fig 15, Stiffness degradation of specimens. 6.6 Effects of column axial load on energy dissipation capacity. The plastic energy dissipation of the specimens is presented in Fig 16. It can be observed that the specimens with column axial load level up to 0.3 caused a decrease of the plastic energy dissipation compared to the specimen without column axial load. However, it was observed that the decreasing rate plastic energy of the specimens with column axial load level more than 0.1 has greater than compared to the specimen with a column axial load of 0.1 and less. For instance, specimens JS4 Sfrc2A05 and JS4 Sfrc2A10 are dissipating less plastic energy at drift ratios of 7.5% by only 0.15% and 0.43%, respectively, compared to the specimen JS4 Sfrc2A0. In addition, specimens JS4 Sfrc2A20, JS4 Sfrc2A30, JS4 Sfrc2A50, JS4 Sfrc2A70 and JS4 Sfrc2A75, are displayed less plastic energy at drift ratios of 7.5% by 4.25%, 4.6%, 4.0%, 3.0%, and 1.79%, respectively, compared to the specimen JS4 Sfrc2A0. This can be indicated that the increasing of column axial load levels are slightly adverse effect on energy dissipation due to axial failure and local crushing of concrete. 7 Conclusions. Based on the nonlinear finite element analysis results of the simulated beam column joint specimens to explore the effect of axial load variations on the seismic behavior of steel fiber reinforced concrete exterior beam column joints, the following conclusions can be drawn. The results indicated that an increase of axial load has a valuable influence to delay the initiation of cracks and damage accumulation. Moreover, when the axial load ratio increases up to 50% of the column capacity, no cracks observed in the joint area, only flexural cracks observed at the beam column interface, and number of cracks in the beam increases with increase of axial load. Increasing the column axial load level from 5 to 30% of the column axial capacity can lead to increase slightly the maximum load carrying capacity of the beam column joints. However, increasing of column axial load level more than 30%, no significant change in the maximum load carrying capacity of the joints compared with no axial load. Increasing of column axial load levels enhances the energy dissipation capacity of joints at initial stage of loading, however, slightly adverse effect when the loading stages further increases due to axial failure and local crushing of concrete. Increasing the column axial load level resulted slightly improvement of the joint stiffness, This is due to the confining action provided by axial load against joint shear, and the development of cross-diagonal cracks was suppressed. However, when the axial load level of more than 50% of the column capacity, the cyclic stiffness decreased slightly due to the deterioration caused by local crushing of concrete in column. Thus, the results indicated that the increase of column axial load improves the confinement of the Sfrc beam column joints. However, a threshold limit could be required.